Alright, so in this video, we're going to be doing some more energy conservation. And for this video in particular, we're going to be looking at a mass of mass M that is sliding down a frictionless ramp that comes into contact with a spring with spring constant K. So the question is asking us to find the mass compression X of the spring. So when we're dealing with energy conservation, especially with frictionless surfaces, we know that the total energy, E total, is going to equal 0 because no energy in our system is being lost. If we did have a frictional surface, however, then we would have to factor that in because when you're dealing with frictional surfaces, some energy in the system is lost due to heat. But for this example, we don't have to worry about that. So we know that our total energy is just going to equal 0 joules. So energy has the units of joules. So here we have an initial situation and a final situation. So initially, this block is just being held there, and then our final situation is when this block slides all the way down and compresses this spring to its max compression. And that's exactly what we're trying to find. So we have, this is the initial situation, and over here when the block hits the spring is our final. So I'll write final right here. So it's important in dealing with energy conservation to define a certain 0. So you want to define a height of 0 somewhere. And for this example, it's more practical to call ground level 0. So we're going to say that the ground is height 0. Okay? Because this block is some distance in the air, it makes sense to make ground level 0. So now to find the max compression of the spring, we have to look at the total energy again because we can't just use 0 joules to find something. We have to relate it to the spring and the mass itself. And how we do that is we write that the total energy is equal to the potential gravitational, we're dealing with the change, so delta of the potential energy due to gravity, plus the change in the potential energy of the spring. And from earlier, we said that this was equal to 0. So we can set that all equal to 0. Alright, so we have the change in potential energy due to gravity plus the change in potential energy of the spring equals 0. So when we're looking at the potential energy of something, especially the change in it, we must look at the initial situation and the final situation. And we know that the potential energy of gravity is just mgh. But since we have a final and initial situation, we must subtract it. So the change in something is final minus initial. So what I'm going to write here is mgh final, and I'll denote that with an F, minus mgh initial. That is what our potential energy due to gravity turns into. So now we have to worry about the potential energy of the spring. I'm going to do the same exact thing because I have to look at the final and initial situations except for the spring now. And we know that the potential energy of the spring is just 1/2 kx squared, where k is the spring constant and x is the compression of the spring. So this equation, we have this plus here, so I'll write this is what our gravitational became. Our plus moves down, and this is where our spring is going to go. So we have 1/2 kx final squared minus 1/2 kx initial squared equals 0. Okay, so now we've analyzed the final and initial situations for both gravity and the spring. Okay, so now we're going to go through each of these and see which ones we can cancel out. Because when we define this height to be 0, we know that something's got to cancel out. Something in this equation has to be 0. So let's look at this first. We have mgh final. Our mass isn't 0, gravity is not 0, but in our final situation, when this spring is at its maximum compression, we know that height is 0 because it's at ground level. We define ground to be 0. So our final height is just 0 meters. So this is going to completely cancel out. Okay? Looking at this one, again, m's not 0, g's not 0, and our initial height is above the 0. So h is going to have a value, so we can't just cancel that out. Okay? So in our final position, when this spring is at its maximum compression, then this x here is at its max. It has gone completely in. So this is a full x. It went from being relaxed to fully compressed. So this x is going to have a value. So we can't just cancel that out. And k is a constant above 0. So we can't do anything with this. But in our initial situation, when the block is just resting on this ramp, this spring is completely relaxed. There is no compression at all. So we know we can cancel this out and make it 0. So dealing with our cancellations, we can say that the total energy is just mgh initial plus 1/2 kx final squared equals 0. Okay? So we have to remember that the question wants us to find the max compression x of the spring. So the only thing dealing with the x here is this. This is what we're looking for. Okay? So all we got to do now is solve for x. So all I'm going to do here is add mgh initial to both sides so that we get 1/2 kx final squared equals mgh initial. Okay? So doing some algebra, you end up with 2 mgh over k, all underneath the square root. And I'll rewrite this 2 equals your max compression x. All I did here was multiply 2 on both sides to give me 2 mgh initial, and then divided the k to get mgh initial over k, and we had an x final squared. So to get the square root, I just square rooted both sides, and that's where this whole side of the equation comes from. And this is our max compression x of the spring.